Okay, so let's begin from where we left off last time. We've been looking at the minimax single facility problem on a tree network, but I stopped temporarily, and then we started looking at the distance constraints problem, where you have a bunch of upper bounds on constraints from each vertex, and we've characterized the consistency conditions for that. So let's recap what we have done, because I'm going to build up on what we have done last time. So we are looking at the distance constraints for single facility case on a tree. Given the numbers Ri, which are the radii for the vertices, the distance constraint problem simply says that you're required to find a point x in the tree, if there's such a point, if it exists, such that the constraints dxvi less or equal ri I 1 up to n, and let's give a name to it. Let's just call those constraints dc, such that these conditions are satisfied. Okay? And we observed first, this is sort of a recap of what we have done. So you've got these things in your notes. Nevertheless, it still helps to write them down, because it's a summary of what we have done before. The first observation we had was the following one. First, we defined a neighborhood with this notation. MVI-RI simply consisted of, or consists of, all points in the tree such that the distance between that point and vertex VI is no more than the upper bound. This is for each I separately. And then we observed that the distance constraints are consistent, meaning that there is a feasible solution. DC is consistent or admits a feasible solution if and only if the intersection of these neighborhoods is non-empty. That's straightforward, because when you look for a point x satisfying all constraints, you are looking at the intersection of these neighborhoods. Okay? So if and only if the intersection is non-empty. And then, with that observation, we started focusing on how we can characterize whether or not a bunch of subtrees intersect or not intersect on a tree. Okay? And that brought me to the so-called Horn's lemma. Well, traditionally it's called Horn's lemma in the literature. I might have called that a theorem, so whatever you want to write it. But let's associate it with Horn. This is back from 1978. And the lemma says the following. Subtrees Si I want to n of a tree T have a non-empty intersection if and only if every pair of them has a non-empty intersection. Of course, whenever the intersection is non-empty, the intersection of all of them is non-empty, then of course it implies that each pair has a non-empty intersection. So that's true for general networks as well. But the other part, when each pair has a non-empty intersection, the fact that that implies that the entire intersection is non-empty is non-trivial. So we had to work on that, but anyway, you've got your proof in your notes now, so we'll just take this as a fact now. This is true only for tree networks because the construction we had applies only to tree networks. Okay? As a good practice for future researchers, you are going to be researchers, most of you, at least as far as I know. Whenever you prove something, go back and go through it to make sure if you're really using the right elements. Sometimes students give me proofs which do not use the facts that we have on hand. They think they prove, but actually, because they did not question it later after proving, they never realize they don't have a proof. Okay? So it's good practice to always go back and make sure that you actually used some of the special properties. Otherwise, you know, if you did not use a tree property, for example, then it should be true for a general network. You should question such things. Okay. At any rate, given this, I also gave you a small lemma. Let's call it lemma 1, even though I did not number these things before. Let's start numbering them. Otherwise, we'll start getting confused after a while. Sure, yes.
Does all the subtrees are neighborhoods?
Not necessarily. No, this is the proof was valid for subtrees, but subtrees are connected. They don't have to be neighborhoods. They don't have to be defined by centers and radii. So the property holds for any kinds of subtrees. There's only one assumption, though, that they should be compact. Okay? In other words, they should have endpoints. Okay? Otherwise, if you just come to an endpoint, get closer and closer to it, but you never get to it, then the proof will have difficulties with that. Okay? So we did make that assumption. So my subtrees are always compact, connected subsets of a tree. Okay? All right. What was I saying? I forgot now. When the question came in. Oh, okay, the lemma. The lemma is simply a connection between neighborhood intersections, pairs of neighborhood intersections, and the distance constraints. So it simply says that for a given pair of indices I and j, this is for fixed pair. We don't have n pairs, or we don't have n choose 2 pairs. Okay? Only one pair, a single pair under consideration. So for a given pair ij, we concluded that the neighborhood vi ri intersecting neighborhood vj rj, well, this is non-empty if and only if the distance between these two centers, centers meaning the centers of the neighborhoods, vi, vj, is less or equal the sum of the radii. Okay? Sometimes I might have stated things differently, but they typically mean the same thing. Okay? The statements may differ from one lecture to another. So if you find a crucial difference, you raise your hand and point it out to me. Otherwise, we might have made a mistake sometimes. Okay? All right. At any rate, this was quite evident. And then I gave you a theorem, which I'm going to call property 6 now, because I think when I started numbering the properties, property 5 was the last one that I had before. Okay? This was from 3 lectures ago. Anyway, I think we can continue with property 6. This is necessary sufficient conditions for DC to be consistent. The distance constraint DC is consistent if and only if every pair of neighborhoods has non-empty intersection let's call that expression 1, which is true if and only if the distance between VI, Vj is less or equal Ri plus Rj for every pair Ij. Maybe the last time I stated it might have been a little bit confusing, but this is the clean statement, okay? So in case it differs from what we had before, take this as the better one.
What does both if and only ifs signify? I mean, one of them is sufficient, or?
That means they are equivalent, meaning that I've got 3 statements here. If and only if means these 3 statements are equivalent, and equivalent means any one of these 3 statements implies any other of the statements. Okay? All right. So the proof, I'm not going to really go into elaboration because it's a direct consequence of Horn's lemma and lemma 1. So let's just give a summary proof. 1 is a direct consequence of Horn's lemma if we define Si to be the neighborhood Vi Ri for every I. Okay? Because every neighborhood is quite obviously a subtree which is compact and connected, and that of course follows from the continuity of the distance. All right. Number 2 is a direct consequence of lemma 1. Oops, let's remove the parentheses here. Yeah, lemma 1. That's the end of the proof. You can fill in the details, okay? All right, so let me take this down now. That's where we left off, I think. And this is sort of a recap of what we have done. Now, what I'm going to do now is to use these properties and, in fact, first give an algorithm or give a constructive method to compute the set of all feasible solutions to the distance constraints. We're going to need that to be able to solve the distance constraints. Then, when we return back to the minimax problem, we're going to still need that to make appropriate conclusions about the minimax problem. Okay? So sometimes you make these drifts from the mainstream, you go to a side stream, you work out the important details, and then come back to the mainstream. Okay? The distance constraints is a interesting problem by itself, actually, without any relationship to the minimax problem, because you can always question yourself, or there's always the question of, if you wanted to locate a single facility which is no more than a certain amount of distance from every demand point, which are the vertices, then where do you locate it? That's a problem by itself. Okay? So don't underestimate its importance. In fact, of course, you can generalize it also to multi-facility problems. For example, find facilities, many facilities, such that every demand point will have at least one of these facilities within a certain distance. Okay? Those are interesting questions by themselves. So we're just looking at the simple case where there's only one facility that you want to locate. Okay, so algorithm. To compute the feasible set of solutions for the distance constraints. The main idea is to intersect the neighborhoods two at a time, or pair at a time. So here's the main idea. You've got n neighborhoods. Okay? In other words, I'm looking at the distance constraints problem in terms of intersection of all these neighborhoods. And what we do is, to find the entire intersection, we intersect these neighborhoods two at a time in an arbitrary order. But each time we find a new intersection for a pair, we delete the old two neighborhoods from further consideration. We just remove them from our list of neighborhoods and insert the new found one, which represents the other two, the old two. Okay? So that will reduce the number of neighborhoods one at a time until, of course, in n steps, you removed everything from the list, and finally you end up with a particular neighborhood. So intersect the neighborhoods one pair at a time until you finally get your solution. That's the main idea. I'm going to give you the full algorithm later, but let's just suffice with the main idea now. So right now, let's just focus on intersection of two neighborhoods. Okay? How do we handle intersecting only two neighborhoods? Forget a set of n neighborhoods. Focus on intersecting two neighborhoods first. If you know how to handle this, then you can repeatedly do this to handle the entire intersection. Okay, so given two neighborhoods, say one at point A or center at A with radius R, and another one with, say, center at point A prime in the tree. We are in a tree network, so you might want to take a note of that, with radius, say, R prime. And what we are going to output from one execution of the main step of the algorithm is a new neighborhood, which I'm going to call A bar, R bar. So we need to compute A bar, we need to compute R bar. Okay? Now, here, of course, I did not make any restrictions on the numbers R and R prime. But if one of them happens to be negative, by definition, you don't have a neighborhood because the distance between any 2 points cannot be less than or equal to a negative number. Okay? In which case, of course, by definition, whenever R is negative, the neighborhood is empty. Okay? So there are a few possibilities here. Even if the radii are positive or non-negative, let's put it that way. By the way, if R is 0, what happens to this neighborhood? It's a singleton. Yeah, it's the point A. Likewise for the other one. So they could be 0. No problem with that. Now, they could be non-negative numbers, but the intersection may still be empty. And we should be able to make that conclusion. If the distance between the 2 points A and A prime is actually greater than the sum of the radii associated with these two neighborhoods, what's the conclusion? Then my composite neighborhood, that's what they are called, my composite neighborhood for this is empty. Because that was the lemma 1. Okay? Whenever the 2 points are farther apart than their radii can reach each other, then you have empty intersection. Remember the strings. That's a good analogy all the time. You pull your strings tight towards one another. They don't reach because the distance is too great between the 2 points. Okay? All right. For the case, the other remaining case, which is less than or equal to R plus R prime, we need to know how to compute A bar and also R bar. I can give you the direct computation, but first, let me take a side step here and just try to figure out what's going on, okay? Because you need to understand what causes the particular type of definitions we have. So this is side step for obtaining insight. For the same problem, what I'm going to do is, let's take a path. This is a path in the tree network which contains the path between A and A prime as a subpath. So this is the unique path between A and A prime. And then, of course, you may extend in different directions in the tree out of that path from either A or A prime.
You mean shortest path by path?
Well, this is a tree network, so shortest paths are there's a single path, so a shortest path is a path. Okay? There's only one path in between a given pair of points. However, this is a path in the tree which contains the portion between A and A prime as a subpath. Okay? All right. So what I mean is, if this is your tree network, if that's my A, this is my A prime. For example, I may be concentrating on this particular path, but the conclusion will be true for any other path that contains that. Okay? So here, from A, one possibility is I go a distance of R units in all possible ways. So I go R units this way, R units along the other portion of the path. And so I want to be here somewhere, to be in the first neighborhood. The second one may have a rather large radius, such as this one, which may go wherever. Okay? Of course, in this case, so we are talking about this being r prime and this being r. When this is the case, what is the intersection? Obviously, this is the intersection in that case. So in that case, you want your A bar to be A itself, and you want your R bar, the output, to be R itself. That's one possibility. Okay? So, in this case, you want A bar equals A, R bar equals R. That's, let's call it case 1. Okay? Case number 2, which is symmetric. So I'm not really going to draw it, but you interchange the roles of A and A prime. So in that case, you want your A bar to be A prime. The larger one is the first neighborhood. And in case 1, the large neighborhood is the second neighborhood, the prime neighborhood. So in that case, we want R bar to be R prime. Just as a small picture, A is here, A prime is here. That's your first A prime neighborhood. The second one is quite large, and it encloses or contains the other one. Okay, whatever. So that's case 2. And case 3, neither of these happen. So in that case, my A is here again. A prime is somewhere here. This has a neighborhood such as that one. The other one, you go R units of distance, but it doesn't go beyond this farther limit of the first neighborhood. So which means that it cuts off somewhere maybe here. Could have also gone here, but it doesn't go further from that particular point on. Okay? So in this case, the intersection is this much. That's probably the more difficult case. So in that case, you want to identify this midpoint to be your A bar. That will be a point along the path connecting A and A prime. And what do you want your R bar to be? R bar will be the length of this. Okay? Well, so R bar will be this much. That's what you want, at least. That's why it's good to draw pictures, then translate them into numbers or whatever you want to work with. So in this case, I don't have much space left here, but I can continue probably. Well, let's just continue here. So A bar is one of 3 possibilities. It's going to be either A or A prime or the point, the unique point on the path connecting A to A prime. So P A prime stands for the unique path connecting A and A prime. Okay? The unique point on the path A to A prime, such for which a certain relationship holds. So we need to define what that relationship is. Okay? But first, let's focus on the first two cases. This is case 1. The second one is for case 2. The last one is for case 3, the pictorial cases. Now, what's the algebraic condition for case 1 in your judgment? So what should I write here algebraically? See, algorithms can only work with numbers. They won't see pictures. Anybody?
If R prime is greater than or equal, actually strictly greater than,
So R prime is greater than
dA prime plus
dA prime.
plus R.
Good, yeah. All right. But you could also have equality. In other words, it may just reach that point, and still your A will be the correct point. Okay. So if the distance between A and A prime plus R is less or equal R prime. Okay? That's the first case. The second case is symmetric. If the distance between A and A prime plus R prime is less or equal R in the second case. In the last case, neither of those relationships hold, so that's the otherwise case. Let me just write otherwise here. Neither of them hold. Okay. The unique point on the path A to A prime for which the distance between the unique point, let's give a name to it. Well, for which the distance between that proposed point and A, the distance between A and the proposed point A bar should be something. What do you think it should be? Say that again. R minus Oh, well, we don't know R bar yet, so you can't use that. R minus R prime plus dA prime. Good, you've got it. Yeah, that's it. How did you get that? You just played with it? Okay, good, that's correct. If you just play with it, you'll get it, I'm sure, everybody. Okay? Let me just make sure it's correct. We don't want to make a mistake on that. Yeah. 1/2 of the distance between A and A prime plus R minus R prime. Yeah. Okay? All right. So that's the definition of the point A bar. What about now the definition of R bar? I'm saying definition, but it's outputting a point or a number. Okay? So in the first case, R bar is equal to R, right?
Was equal to R for the case 3, not dA.
Let me just check. No. I have that. You wanted to have R bar here?
Yes.
No, it will be the distance between A and A bar. Does that check? I don't know. We can check that later. This is correct, okay? All right, so in the first case, this is this situation. Wait. Plus R is less or equal R prime. In that case, it's R. In the second case, it's R prime. In the third case, it's going to be R plus R prime minus distance between A and A prime over 2. If you don't believe me, you work on it at home and convince me that this is not correct. Okay? It is correct. All right. So let me state a property 7 here. I'm going to state this without a proof because the pictures actually explain what's going on, so you can work out the most difficult case, the third case, on your own at home if you have some doubts about it. But the question is, for a single pair of neighborhoods, their composite single neighborhood expression is defined by A bar and R bar. That's the claim, and that's a provable fact by just investigating the pictorial situations that we had. Okay? Okay. So, let me give you the sequential intersection procedure now. That's the algorithm. The sequential intersection procedure simply does the following. It defines an initial list at the beginning, which consists of the neighborhoods VI, MVI, RI. And it simply pick any two neighborhoods from the list, and then compute the composite neighborhood representation of their intersection. What's the composite neighborhood representation? It's what we have done over here in computing A bar and R bar. Just take a note of that. So this is, in fact, composite neighborhood representation for the intersection of two neighborhoods. Okay? All right. So pick any two neighborhoods from the list and compute the composite neighborhood representation of their intersection. Insert the composite neighborhood representation into the list and delete both members of the last pair from the list. That's the main step. And then you stop when there's a single neighborhood left. Stop when list contains a single neighborhood. And that last persisting neighborhood will be your final answer. So, whatever neighborhood you ended up with in the list, that one will give you the entire intersection of all of them. Okay?
Solve the original problem.
Pardon? Say that again.
This allows us to solve the original problem in n times the longest path in a graph.
Well, first of all, we have a tree network. This works only for a tree network. Okay. This, you execute the main step n times, because each time you reduce the number of neighborhoods in the list by 1. So in n-1 steps, you end up with a single neighborhood. And each step requires the computation of A bar and R bar, which can be done in linear time. Well, actually in constant time, because everything is given. Okay. Of course, you need to have a representation of the tree in the computer in some way. There are various ways of representing trees, but that's besides the point. So this is a ON algorithm. It does the job in ON time. Okay? Is that what you were saying? Essentially.
I thought that it was also for general.
N squared. Oh, okay. No, this is only for tree networks. Everything I'm proposing until now is for tree networks. Because Horn's lemma works only for tree networks. Otherwise, it won't. Okay. All right. Let's take a 10-minute break now, and we'll do some additional stuff with this.